everyone, welcome back to week 3. So we are almost to the halfway point. We're going to cover chapters 6 and 7 this week and then do your midterm. Your midterm is going to be open book, open note, but please understand that doesn't mean you can copy paste anything from the internet. I expect you to submit your own work. So we're going to try and move through chapter 6 and chapter 7 over the next 2 days to get you all ready so that you have plenty of time to study for and then take your midterm. So chapter 6 talks about Earth's interior and earthquakes and mountain building process. So let's get started. So just a quick breakdown of the Earth's actual composition. So starting from the surface and working our way in, the Earth's outer material is called the crust. And the crust is anywhere from 3 to 50 miles thick, thinnest under oceanic plates and thickest under continents, and is extremely rigid material. Beneath the crust is the mantle. This is estimated to be about 1,800 miles thick. It is ductile and very plastic. It's very easy to manipulate it and move it, but it bounces right back. And the strength actually increases with the depth, so it's very weak up at the surface and much, much stronger the further down you go. And then the outer core is estimated to be about 1,400 miles thick, and it is comprised of liquid iron and nickel. And the movement of this liquid iron and nickel is what is believed to generate Earth's magnetic field. And then finally the inner core, which is believed to be a sphere with a radius of about 750 miles, so about a 1,500 mile diameter. And this is liquid iron and nickel. I'm sorry, not liquid, that's a typo. It's solid iron and nickel, and it rotates independently of Earth's rotation. So here's just another image showing the breakdown of Earth's interior. It's kind of hard to see. Hopefully it shows up better in the PDF I posted for you all. But this just shows the convection movement of the liquid outer core and the mantle, and we'll discuss how that impacts the crust or the Earth's surface. So how did the Earth's layers form? Why does the Earth have these very distinct separate layers? So to understand that, we have to go back to the actual beginning of the Earth. So a little over 4.5 billion years ago, the Earth was nothing more than just a bunch of cosmic dust that was coalescing around a new star. So our sun wasn't fully formed yet, and it was just this huge cloud of dust all around it. And then the debris started attracting to one another and sticking together and building these larger and larger debris globules, basically. And this debris would gather together more and more to start to coalesce into planetary bodies. There you go. At the very beginning of Earth's history, it's believed that a planetoid about the size of Mars actually hit Earth at a low angle, and Earth was still so hot and still so loosely coalesced, is that a word? That a significant chunk of the material is actually believed to have been ejected away from Earth. And then Earth basically, after that impact, it's like I said, it's still hot, it's still very liquid, so it actually begins to remelt and reform into a sphere after that impact. And then the moon is believed to have been formed from the debris that was ejected from that impact. And we'll discuss that more in chapter 15. So the Earth is this big, hot, liquid ball of all kinds of elements and gases. And the surface, the exterior, is going to cool first and form a crust around the Earth. This happened 4.4 billion years ago. And as this occurs, the heavier elements coalesce or sink. So they're sinking towards the center, right? Because heavier things are gonna drop. And as this happens, you get your basically your separation of elements. So you've got your iron and nickel, very dense core, and then your outer core, and then your lighter mantle, all encased within your crust. But how do we know it's layered? How are we determining this? Just make it up? Are we able to see? Are we able to just take a slice of the Earth and see that this is a composition? No. The deepest explored caves on Earth are only about a mile in depth. The deepest mine is only 2.5 miles, and even the deepest well on Earth is only 7.5 miles deep. Remember we said the Earth's crust is anywhere from 3 to 50 miles thick. Okay, so you can see that the only way we would have even penetrated the crust is with this well. Well, this well is still located on a peninsula, so it's still located on continental material, which is not very thin. The thinnest material tends to be oceanic material in the abyssal plains. So we haven't even broken through the crust with these depths. We know this by indirect evidence, primarily from the movement of seismic waves as they travel through the Earth. So seismic waves travel faster in denser material and slower in less dense. There are two types of body waves. Body waves are what moves through the Earth. These are the P waves. These are the compressional, and they are the fastest. So compressional, we're talking about a wave will compress like this and then bounce forward, and compress like this and bounce forward. And I don't think you can see my hands anymore. But so you get it. It's like if you compressed, like if you pushed together a slinky and then let it go, and it would bounce apart, right? S waves travel up and down along a wave path and cannot travel through liquids. So S waves are like if you took a jump rope and just shook it up and down, and it's going to make that up-down wave motion, and that cannot move through a liquid. There are also two types of surface waves. The Rayleigh waves, these are basically rolls. They move in a circular motion, so it's actually an orbital motion of the Earth's material as the energy passes through. And then love waves. These are side-to-side motions as a wave passes. Okay, so we have four very different styles. P waves are compressional, S waves are up and down, Rayleigh waves are orbital, and love waves are side-to-side. Okay. So here's a good example of a seismic or a seismograph reading. And it shows the P waves are the fastest, and they will always arrive to your seismic station first. So that's going to be that first blip on there. And then you have a period of time after which your S waves begin to arrive. And closely following your S waves are going to be your surface waves. Now, like we said, S waves cannot travel through liquids, and P waves are the fastest. Okay, and the Rayleigh and love are surface waves. So if we're looking at an earth, you can't see me pointing, I'm really sorry. If we look at an earthquake that originates in the ground under house A, we want to know which of these seismographs down here match up to each of the houses. So for house A, it is located right above the epicenter of the earthquake, basically. So your P waves are going to arrive almost immediately after this earthquake begins, right? Because they're the fastest waves. Well, the only one that has something occurring right at the beginning of the earthquake is right here, right? And so we've got our P waves, and then our S waves are going to come right after because it's so close that that speed differential between P and S don't really matter. And then your body waves, which are always much larger in magnitude on the seismograph than the others, are going to arrive right after that. So we basically got our P, S, and body waves all one right on top of the other. So then we go to house B. So we've got waves moving through the interior. Okay. So we know that our P waves get there before our S waves, which get there before our surface waves, right? So here we've got two where our P waves show up first, followed by S waves, followed by surface waves. So which one do you think it would be? So here we've got our P wave showing up fairly early on, a period of time before an S wave, and then another small period of time before our still large magnitude surface wave. See how that's still a significant magnitude here? So our house B is going to show up right here. We're still getting all three waves. They're still all showing up at the house with a sizable measurement. But they're a bit more spread out now because of that speed differential. Now house C, so we've got our earthquake moving through, and it might just glance off the outer core here. Our P waves might just glance off the outer core here, our S waves might just glance off, and then our surface waves going all the way around. So that one we've probably got this. We've got a slightly longer period of time than house B. Our S waves are still arriving because we're still moving through the mantle. And then our surface waves, you can see the magnitude is decreased. Now house D, we're going to be going through the core, or through the outer core to D, right? So because of this, it's got this huge distance to travel, so our magnitude is getting even smaller. We see a little blip here for our P waves. But then you see this giant opening, there's no S waves there. It's because the S waves, once they hit the outer core, they just stop. They don't move through liquid. S waves terminate right at the outer core. So then we've got this huge period of time while our surface waves travel all the way around to D. Okay, so see that breaks it down for you. It just kind of shows you, so you've got your PNS, your PNS, your PNS just barely missing the inner core, PNS here, but then it's just the P waves moving through the inner core to house D. Now I'll talk more about that when we get to the section on earthquakes, but for now let's talk about rock deformation and mountain building. Okay. So what does the presence of fossil marines found on present-day mountain ranges suggest to you? For instance, in the Canadian Rockies, there are trilobites found up in the high mountain ranges. Ammonites found in the Andalusia in Spain, elevation of approximately 4,000 feet. These are sea mammals. These are sea life. What would they be doing up on top of a mountain range? Sorry, 1 second while it loads. Okay, so when we talk about that, we need to understand rock deformation and mountain building process. So rock deformation is part of the process that actually results in this sea life on mountaintops. Rock deformation can occur on scales from just a few inches to hundreds of miles. So for instance, the image here shows internal rock deformation, folds that are exhibited within a single rock unit, as evidenced by the dime right here to give scale. This is a small outcrop, probably along a roadside, a couple meters tall, showing some really involved folding of rocks. This is a much taller section where you can see a folded section of rock. And here is actually an aerial image of the Susquehanna River Valley. This is just north of Harrisburg, I think. And you can actually see how these rocks are folded and manipulated because of the changing elevations here. So to understand rock deformation and how marine life ended up on mountains, we need to understand the types of deformation. So there are 3 general types. And most crustal deformation, most mountain or most rock deformation occurs along plate margins. And this is because plate margins are the areas with the highest amount of energy and pressure and stresses occurring. And that's what's necessary to really manipulate these rocks. So stress is a force applied to any given area, and these plate margins are areas where you're going to experience the force on a scale large enough to manipulate these rocks. So there are 3 types of deformation. You have elastic, ductile, and brittle. Elastic means the rock returns to its original size and shape, so it basically bounces right back. So it's one where either the stress applied isn't very high, or the rock material is still supple and not quite liquefied enough that once that stress is removed, it's allowed to relax and go back to its original place. Ductile is where rock flows once the elastic limit or the strength of the rock has been passed, you start to get that ductile deformation where it starts folding or manipulating, but it doesn't break. So that's how we get those really nice folds that we see. Like if you... So if I took this piece of paper, that's a piece of paper. Let's find a new piece of paper. So if I took this piece of paper and applied a bit of stress and then stopped the stress, it would bounce right back for elastic. But if I took this piece of paper and applied a stress and then I stopped applying the stress, but my rock has met its elastic limit, it'll stay here. This is ductile deformation. And then brittle deformation is where the rock would eventually reach its elastic limit and then it would break somewhere, along this folding section here. So the deformation that creates these wave-like undulations are called folds. And folds result from compressional stresses that shorten or thicken the crust because they're pushing in, right? So if I'm pushing this paper in, I'm making it shorter, and I'm making it thicker, because now all of a sudden it's, you know, how many times taller? 2, 3 times? I guess it's a lot more taller than that, but it's much taller now because I've shortened it, and all that material is accumulating in the middle, right? So when we talk about types of folds, there are actually a number of ways to classify them. So when we talk about folds, you can have a number of features. The first is an anticline, which is an upfolded or arched rock layer. So this right here in the middle, this will be an anticline. If we have ductile deformation occurring where it downfolds, this would be a syncline. Okay, so anticline is up, syncline is down. Now, the anticlines and synclines can then be broken down into smaller categories based on their symmetry. So if you have an anticline that is perfectly symmetrical on both sides, this is about as close as I can get with a piece of paper. See how this is symmetrical? This would be a symmetrical anticline fold. But if you have stress that is applied with a slightly higher force on one side than the other, see if I can do it with paper. There we go. Okay, pretend that's my force. Okay, this would be an asymmetrical fold. If I drew a line through that axis plane right there, it wouldn't be symmetrical, right? There's differences. And then if you get where one side has much more force than the other, so it pushes it way, way over to the point where it's almost flipped. Do you see how it's almost flipping over itself now? That's called an overturned fold because it's literally about to just kind of overturn onto itself. So then the same can be said with a syncline. You've got your symmetrical syncline, you've got an asymmetrical syncline, and then you can't have an overturned syncline because it's already a trough. Then it's usually associated with an overturned anticline. So this is showing an overturned fold. You see how it's about to basically flip over onto itself if it pushed forward anymore. And it's also important to note that a lot of ductile deformation occurs in conjunction with brittle deformation. The rock can't always handle all that stress, all that energy along the whole plane. It usually has to release that energy somewhere along the point. So we have the energy creating these overturned folds, but at some point that energy was too much for the rock here. It had to dissipate it somehow, and it actually just broke that rock apart. We've created a fault system here. Some other types of folds that we will discuss are, you know, anticline and synclines were kind of mirrors of each other. So this is something similar. We've got a dome, which is super hard to do with paper. It's basically like an upwelling in the middle of the earth. It's equal all the way around. Okay, like I'm poking it through the paper. It's a really great example, right? And a basin is downward in all directions. Okay, so upwarping in all directions or downwarping in all directions. And a dome then, as it's upwarped in all directions, the stuff at the surface erodes. Stuff at higher elevations tends to erode faster. So what happens is the stuff at the center is the oldest material, and stuff at the edges are the younger material, like you see in the image here. And in a basin, you've got the downwarping. And what you'll have here is your oldest material is at the edges, and your youngest material is at the center. So domes, your oldest material is at the center. Basins, your youngest material is at the center. Both can occur local or regional scales, and they don't always circular. They can also be ellipsoidal. There you go. So this is an example of the Black Hills of South Dakota that are actually an ellipsoidal dome. So we have our Dakota sandstone around the edge, and then our ellipsoidal dome or upwarping. So as it did that, we have some preferential weathering of the sandstone where it started to upwarp, and that has exposed our limestone plateau. And the interior was upwarped even more, and with even more preferential erosion, exposing our crystalline interior. So here's just a cross section showing your much younger sandstone and your much older Precambrian granite interior. Elliptical basin. Lake Superior is actually an elliptical basin that has now been filled in. But if we took a cross section of that, we'd have our much older Precambrian rock at the edges and underlying all the much younger lake sediment deposits. Okay. Additionally, not all folds are seen at the surface. there is plenty of deformation and folding that has actually occurred beneath the surface that we're not able to see. And to actually experience this, man-made seismic methods are used. Ground-penetrating vibrations are generated, and the way their waves bounce off the rocks give us a graphical image of the subsurface, allowing us to see any folding in the interior. So this becomes important because, and if you move on in geology, you'll learn this in sedimentology and stratigraphy, but natural gas and oil move through sandstone and shale units, but they also tend to accumulate in the peaks of these folds here. Because of how light they are, they'll accumulate up in these peaks here. So if you're going to drill for oil, drill for gas, you want to find subsurface domes of sandstone, and that's where you're going to want to drill. That's where it's going to be most productive. So these seismic tools are used to try and find these domes here to develop oil and gas wells. So what kinds of folds are these that are labeled? So A, C, and E would be anticlines, right? They're pointing upward. B and D are synclines. They're all flexed downward. So as you can see, B, C, D, and E are not symmetrical, right? If you still can't see my hands. I'm trying to point to the screen. If you drew a plane through their axis here, it would not be the same from one side to the other. A is symmetrical. See, if we drew a line right here, it's exactly the same on each side. And how would we know this from evidence on Earth? So geologists take measurements called as the dip and the strike, field measurements, and then we discuss relative ages of rocks to determine what limb of a fold we're observing. We'll talk about age rocks later, but we're going to be moving into dip and strike in a minute. Let's move on to brittle deformation first, and then we'll get back to that. So brittle deformation are faults. Faults are just fractures in rock in which displacement has occurred. Sudden movement along these faults are what cause earthquakes. There are two types of faults. There are dip-slip faults, where the movement is parallel to the dip, the photo at right. So basically, really, I used to have like these really cool books to show it, but so if you had like two parallelograms and got their sides, you have one side drop down in relation to the other. So that's a dip slip. You've got that angle, and it's sliding right along that angle vertically. Whereas strike slip faults are faults where movement is parallel to the strike of the fault at the surface. So it's moving at the surface, you know, along like this, side by side. There we go. Okay, when we talk about faults, and we also use this to determine what side of a fold we're on, we use what's called the right-hand rule to determine the direction of a dip and the strike. So if you place your right hand, here's my plane in question, okay? You place your right hand on the plane in question, point fingertips down the dip of the plane. So here's my plane. Measure the dip amount and direction with a protractor and compass. So I would just put a protractor here to determine my angle. So, you know, I'm 45 degrees from horizontal. Sure. And then your strike, if you extend your right thumb perpendicular to your fingers, where they are resting on the plane of the dip is your strike. So you would then measure that with a compass. So we're going to assume that if I'm pointing at myself, I'm pointing south. So I'm dipping at 45 degrees with a strike south. You wouldn't say south, you would use like a compass degree, like 312 or something. But I don't have a compass with me. Sorry, guys. So using the data, what kind of fold is indicated in the diagram below? So here we've got our right-hand rule showing one side of the fold has a strike of 36 and a dip of 216 degrees. So we're dipping 216 degrees on one side and we're dipping 37 degrees on the other side. So we're looking at an anticline that is almost an overturned anticline because the huge change in degrees between these two on either side. So these measurements are one side of the fold and another. Okay, we're going to skip this because this is really hard to do on an online lecture. There's not going to be any sort of questions on measuring this on your exam. It's just something good to know. If you move on in geology, you'll learn this in more detail and how to apply it out in the field later on. So, back to brittle deformation. So when we talk about fault displacement now, so we talked about there's strike slip and dip slip faults. So we talk about a dip slip fault. We discuss it by talking about the sides as the footwall block and the hanging wall block. This is because miners actually used to excavate tunnels along the surface of a fault because mineral deposits were often preferentially found along these fault planes. So when they did that, if you look at the image here, as you dig a tunnel in to the Earth's interior, no matter where you are along that fault line, you're always going to be walking on one half of the fault and hanging your lantern, hence the name of the hanging wall, hanging your lantern on another half. See, there's not a whole lot of space right against the wall here to hang your lantern on that side, so you're not hanging on the footwall, and there's not a whole lot of space to walk on this side, so you're not going to be walking against the hanging wall. So your footwall block is the one you're walking on, and your hanging wall block is the one you're hanging your lantern on. Now in a normal fault, this is where the hanging wall has moved down relative to the footwall. So if you look here, this piece of rock used to be for this piece of rock, and then this whole block just slid straight down. So we've got our footwall block that is now higher than our hanging wall block. But if you drilled a hole right here still, see if you're walking in, you'd still be walking on the footwall and hanging on the hanging wall. A reverse fault is where the hanging wall has actually shoved up and over the footwall. This is the result of compressional forces, so forces pushing together, whereas a normal fault is actually from extensional forces. So all of a sudden you've got this release of pressure, so you're going to have material trying to expand and slip down. And do you see any evidence of original faulting in the picture on the left? If you look here, it looks like there's a bit of faulting that has occurred here too. So this shows extensional forces creating your normal fault, where your hanging wall block actually slips down in relation to your footwall. Your reverse fault, compressional forces actually force your hanging wall up over your footwall. And then we have what are called thrust faults. These are reverse faults, so they're the same compressional stresses, but these are ones where their fault plane dips at an angle less than 45 degrees, so it's a much shallower angle that at which point it converges up. So this is just a exercise in fault displacement. So trying to determine what kind of faults you see here. So you see here we have a normal fault. This block dropped in relation to that one. Here it looks like we might have another normal in relation to this. There's a thrust fault in here. Let me see if I can find it again. There's our normal, all more normals. Oh, no thrust fault. These are all normals. We have a different image. So this is just showing some faults in western New York. These are all faults that we know about in this region. There are two fault zones near Jamestown. The Clarendon-Linden fault zone is actually seismically active, and it has a very complex history, and this is actually up north. Is that near Rochester? I think it's still west of Rochester, right? Secondly are the Bass Island fault zones. These are not seismically active. They're dormant right now, and they do not reach to the basement rocks. So when we're talking about basement rocks, we're talking about what are called Precambrian rocks, so typically igneous granite material. Oh, sorry guys. Oh my goodness. So this is just showing earthquake magnitudes over, I'm not sure how many years. But so there have been, a number of recorded earthquakes around the western New York region in recent history due to these small-scale fault zones and fault regions. So like I said, the Clarendon-Linden fault system, it has a strike north Okay, so they tend to run north-south. It's about 20 to 30 miles east of Buffalo. Okay, much closer to Buffalo than Rochester. They've reached up to a 5 on the Richter scale, but that hasn't happened since 1922. And these are extensional or normal faults. Okay, so the hanging block drops down below the normal or the wall. They originate in the basement crystalline igneous and metamorphics and extend to the surface. So these are very large vertical systems. But there's no significant production of oil and gas along the fault zone. The movement most likely caused any oil gas traps that existed to actually leak to the surface. The Bass Island faults strike northeast under Bemis Point on Lake Chautauqua. There's no known seismicity. Like I said, it's dormant at this time. These are thrust faults. These are compressional caused when Africa collided with North America, to give you an idea of how old these are. And they only extend through the Ordovician shale and Silurian salt beds. It doesn't reach all the way to the basement, and it also doesn't reach all the way to the surface. They're contained within a middle section. It does provide traps for oil and gas. They were actually successfully drilled in the 80s and 90s, and the largest modern oil wells in New York have been discovered there. It's a good place for the Utica Shale, and I'm not sure if the Marcellus Shale extends that far, but the Utica Shale definitely are extremely good oil and gas reserves in the western New York area. And actually, if you go to Lake Erie just outside Fredonia, if you go to, I think it's Lake Erie Park or Fredonia Park, it's right near there, you can actually see some of the shales coming out right at the lake surface, and if you crack those shales open, you can smell the hydrocarbon trap within those shales as they come to the surface. So here it's showing it trends, northeast. And this is just showing an example of the thrust fault subsurface as has been collected from some of the oil and gas exploration drills and some seismic data. Okay, strike slip faults, also known as transform faults. These occur when two blocks move past each other along the strike of a fault. So this is horizontal movement. So when you look across, the way these are categorized is if you stand on one side of the fault and you look across to the other, you categorize it based on what direction it looks like the fault blocks have moved. So for instance, in the image on the right, if we're standing here, the image or the block directly in front of us looks like it has moved to our right. So it's a right lateral strike slip fault. Okay, and if you're standing here, it looks like the block right in front of you has moved to your right. So it's a right lateral strike slip. You can also call it, if you're standing here and it looks like everything's moved to the left, then it is called a left lateral strike slip. They're extremely common along mid-ocean ridges. Transform faults are common around mid-ocean ridges. So if you look, you see how the mid-ocean ridge isn't just a straight line, it kind of disjoints off as it goes, because the rate of separation, the rate of magma introduction, isn't always exactly equal. So one side might start growing and accumulating faster than the other side. So it's going to start creating this buildup of friction and force as it tries to expand the ocean plate, and it causes these sections where it actually slips past each other and breaks apart because there's so much energy buildup there as the plate is trying to expand. Finally, into mountain building. So here we just have a look at some of the major mountain ranges across the globe. And I want to note the north-south trends of the mountains in North and South America, specifically the North American Cordillera and the Andes, and the east-west trends of the mountains in Eurasia. Okay, these are important trends to acknowledge. We also want to look at these yellow spaces called the shields. These are exposed Precambrian crystalline rocks. These are extremely old, extremely stable rock material. Okay, the Canadian Shield is one around the one closest to us. There is very little tectonic activity there. It is extremely stable. There's not a whole lot going on. So when we're talking about mountain building, we're actually discussing what's called erogenous, or the process that produces a mountain range. Subduction and plate collisions create most of our mountain ranges. That's why we have this this north-south orientation here, because we have that Pacific plate and North American plate colliding. And our east-west trending ranges here, because we have the plate that Africa is on, colliding with the Eurasia plate, creating that mountain range as they come together. And the Himalayas especially, that Indian plate is actively shoving itself into China and creating this uplift of the Himalayan mountain ranges. So how do they develop? Continuous subduction of lithosphere results in the buildup of thick continental crust on the overlying plate. So as we have our ocean plate subduct, it starts to melt off, and our lighter materials, our more silicate materials, come to the surface and break through. They're deposited as intrusive igneous material, exposed as extrusive igneous material, start to build these volcanic island arcs and systems. Oh, sorry. Island arcs can be joined together to create a terrain, not the same as terrain, T-E-R-R-A-I-N, which is land in general, but can create a terrain of continental crust. This is a fragment that is transported by plate tectonics. It moves with the plate, and they can be microcontinents, islands, or island arcs. The Andean mountains were actually built, like I said, by the subduction of an oceanic plate beneath a continental plate. So we already have the continental material there. We're not building a continental terrain or an island arc. This is where you have your oceanic crust subducting beneath the continental crust, and as that partial melting occurs, it introduces that magma, that heated material, up to the surface, where it starts to create plutons that are pushing the surface up, volcanic activity, which is developing the surface. But additionally, you get all this like surface deposits that are actually being scraped off the descending plate here and accumulating and building up ridges in this region too. So that's how we get what are called uplifted accretionary wedges. That material starts to uplift and accumulate to the point where it creates what looks like a small mountain range. Plutons and batholiths. Batholiths are just a collection of plutons. Begin as magma, which crystallize into intrusive igneous rocks without ever breaking through the surface. So these come up into the mountain range and crystallize before they ever reach air. The North American Cordillera Range, this is slightly different. So what happened here is we have a subducting oceanic lithosphere that actually brought island arcs and a microcontinent to collide with the western edge of the United States, the North American continent. And as it collides, you start to get basically an accretion of those island arcs and that microcontinent, until all of that collides and accumulates and builds up here, shoving all of that former island or oceanic material up onto the continent and accumulating into the Cordilleran Range. So this just shows terrain that have accreted into North America in the last 200 million years. There's a significant number that, as the plate tectonics have progressed, have actually gone from microcontinents that existed out in the ocean to being part of the North American makeup. The Himalayan mountains. This is a unique group. This is continental collisions. So here we've got our continental crust of India, actually colliding with the continental crust of Asia. And as it collides, that crust material has nowhere to go. It's too light to subduct with the oceanic lithosphere here. So it just kind of crushes together and keeps crushing up and shoving up until it builds what's called the Himalayan mountain range. We do get sections of material called ophiolite. This is mafic igneous rock from the continental crust. So when they first start to converge and collide with each other, they trap a little bit of oceanic crust right there. So that gets stuck and detached from the subducting plate and actually hangs out at the surface, which is how we have evidence of that collision, because there is no other way that ophiolite, that oceanic crust, could have gotten here behind the Himalayas in the Tibetan Plateau otherwise. Okay, so we've got that ophiolite hanging like right back here. How else would have gotten there? It has to be from this continental collision. Okay, I will post the link to that video. That is the end of Earth's interior and mountain building. And now we will move on to earthquakes. Let's see if I can get that. Sorry. Here we go. Move that. Okay, here we go. So we're going to move on to earthquakes. We talked a little bit about that when we talked about the waves and how they move through the Earth's interior. But let's talk about more about earthquakes specifically. So what is an earthquake? So in short, an earthquake is just the vibration of Earth caused by a very sudden, very large release of energy. So the ground shaking is typically caused by a sudden movement of one block of rock slipping past another along fractions in the Earth's crust, that we talked about. And the destruction can lead to structural damage, changes in water table, complete changes in landscape, and loss of life. Additionally, earthquakes that occur at sea can create destructive tsunamis along coastal regions. So, when we talk about how an earthquake forms, let's see if I have a good... I don't want to break anything. So, we have our starting point, where you have your earth material at a stable kind of situation. There's not a whole lot of energy buildup. It's at equilibrium. There we go. So it's basically if you're holding a stick, you're not putting any pressure on it. So over time, something happens, the Earth's plates are moving, and so all of a sudden the crust material is getting forced in one direction or another. So you can see here, the land is starting to warp, and it's still in a ductile phase. It's still connected, but it's really starting to stress that relationship. It's building up a lot of energy, a lot of friction right here. Until that force applied is just too hard, too much force, and it can't handle it anymore. So it breaks along a region of lowest strength, highest stress, and all of a sudden we have these plates sliding past one another. Like if you bend a stick past its flex point. And once the strength is exceeded, the slip along a fault produces an earthquake. Because all of a sudden you've got all this energy all built up, and it needs to release. Just slide past real quick to release that energy. Now that energy's gone, but it had to be dispelled somewhere. It's dispelled out into the crust. It can occur along transform plate boundaries in faults or along subvertical plate boundaries like subduction zones. And the greater the friction, the longer it will take for the rocks to slip, and the higher the stored energy that will be released when they do slip. And the slippage can actually occur in cycles over time. The time between past earthquakes can give an estimate when a future earthquake can be expected, but there is no way to pinpoint exactly when one will happen. Most earthquakes occur at tectonic plate boundaries, and the deepest earthquakes occur in subduction zones because you've got the earthquakes occurring, you've got a plate subducting. You have material down here that's displacing material, crustal material here that's displacing mantle material, and it's going to cause that change in energy at depth. So this just shows the worldwide earthquake distribution in relation to the to the global plates. So you can see that the concentrations are extremely high along these plate boundaries. You know, they pretty much follow them exactly here. So what happens at subduction zones to cause this? So as a plate collides with the continental and starts to subduct, you're getting this buildup of friction right here. So you see this? You've got a lot of friction, a lot of slippage occurring. So you're going to have a lot of energy buildup right there. You're going to get a lot of release of energy. So you're going to have significant earthquakes occurring at this convergent boundary, as these plates are coming together. You've still got oceanic crust and continental crust and the lithosphere rubbing against each other here. There's still a lot of energy, still a lot of friction. So you're still going to get earthquakes occurring at depth as these materials move past each other. Now, once you move through the lithosphere into the asthenosphere, so now we're into the upper mantle, you've still got a lot of release of energy from that plate movement. So you're still going to get them with depths moving in horizontally under our South American plate. And you can get them, you know, up to like 500-700 kilometers deep as this oceanic lithosphere is moving through the asthenosphere, as it's displacing internal material because of the energy, because of the forces and stresses being applied as it subducts before it begins or before it undergoes its complete melting. So when we talk about earthquakes, we also talk about the energy waves associated with them. So the waves, move, and as they move, we discuss them based on their amplitude or frequency. So an amplitude is the maximum change in energy condition over or under an equilibrium position. So it's how high or how low something goes above stationary, basically. Whereas the frequency or the wavelength is how long it takes for one successive high or low peak to pass the same point. So what changed in the graphs between A and B? Well, here we have condensed the wavelength, right? Our amplitude is still the same, it's still the same height, but our wavelength has become much shorter, right? We've compressed the same graph down. Whereas in C, our amplitude is much lower. See how it doesn't come up as high or down as low, but our wavelength is still the same. So, like I said, earthquakes release this stored up seismic energy, and they travel in all directions from what is called the focus or the hypocenter of the earthquake. So the hypocenter is actually where the earthquake occurs. That's where this release of energy happens. When we talk about an earthquake epicenter, which is what you usually hear, this is actually the point on the Earth's surface that is directly above the hypocenter. So if we went vertically straight up from our hypocenter, that's our epicenter. Whereas, it's not, if we followed the fault line up, that's not where it is. So even though our hypocenter occurs on the fault, our epicenter could actually be a couple miles away from the fault, based on how deep this hypocenter actually occurs. So like we said, there are seismic waves that are the elastic energy that is released by this movement, and they are measured by a seismograph or seismometer. Like I said, there are two types, the body waves, those are the P and the S waves, and surface waves, the Rayleigh and the Love waves. So the P waves cause the ground to be compressed and expanded, and are the first to reach the station. S waves cause it to move up and down like a jump rope, and cannot travel through liquid. Surface waves, we talk about the Rayleigh, are this circular motion, so it makes it actually look like an ocean wave is moving across a landscape. So if you've ever seen a video of an earthquake like that, it literally looks like a wave moving across the surface. These have much higher amplitudes, and their vibrations last longer. So these are the ones that do the damage. So when we talk about damage caused by earthquakes, it's caused by these Rayleigh and Love waves. Geologists and geophysicists have created a model of the Earth's layers and the speed at which these waves should travel through them. And using this, we can actually create seismic travel time graphs. So a seismic station determines the time interval between the first P wave and the first S wave, like we looked at earlier. And then a circle with the radius using the distance indicated is plotted on a map. So the earthquake could have occurred anywhere along the circumference of the circle. But how do you determine where the epicenter is? So if we've got this whole circle, well, where's the epicenter on that circle? So this is why you need at least 3 recording stations to locate an epicenter, because you have a circle from station A, and a circle from station B, and a circle from station C, and where they all intersect, that is where your epicenter is. Okay, that's the one point they all have in common. So, steps to locating an earthquake. So here we get seismogram readings. So we need to get at least 3 readings from 3 different stations, right? And looking at this, we've got our first P wave that arrives at our station. And then 5 minutes later, each of these lines is a minute, so 5 minutes later our S wave arrives. So our station is, based on the amount of time it takes the S wave to show up after the P wave, that tells us that our epicenter is 3,500 kilometers away. So if our S wave only took 2 minutes to get there instead of 5, so our P wave and then 2 minutes later our S wave, our epicenter would only be 1,000 kilometers away. 5-minute interval means it's 3,500 kilometers away. So we have our three graphs. We have our first P wave shows up, and our first S wave shows up. So on A, we have 1, 2, 3, 4, 5 minutes. B, we have 1, 2, 3, 4, 5, 6, 7 minutes. Let's see. Right here. And then C, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost 11 minutes. Okay, so this shows you the three different travel times. So you would plot them on the graphs. So A, B, C. Here we go. And this shows us what radius circles to draw. Yeah, radius circles. So A would have a radius of 3,500 kilometers, B would have a radius of 4,900, and C would have a radius of 8,200. So then we go and we find where these reading stations were. So our reading station A was in India, with a radius of 3,500 kilometers. B was in Northern Australia with 2,900? 4,900. And then C was in China with a radius of 4,900. And you can see they all come together right here southwest of the Philippines. So that is our earthquake epicenter. So then earthquake size and strength is measured in two different ways. First is the intensity. This is based solely on subjective observations of damage using the modified Mercalli scale. And this scale uses Roman numerals. It runs from 1 to 13, and 1 to 12. And so a 1 is not felt except by very few under very favorable circumstances, so on sand or really unstable surface to begin with. These are usually only identified with scientific measuring equipment. All the way up to 12, which is where damage is total, waves are seen on the ground surface, objects are literally thrown up into the air. It's basically loss of all materials in life. And then the one you're probably more used to is called the magnitude. This is based on an estimate of energy released using the seismograph records. This uses the Richter scale. So each level of an earthquake causes 10 times greater ground motion than the level above it. So it's a log scale. So earthquake with a magnitude of 2 is 10 times greater than one of the magnitude of 1. Magnitude of 6 is 10 times greater than a magnitude of 5. A magnitude of 5 is 100,000 times greater than a magnitude 1. And here we've got description, average per year. So magnitude of 2 to 3, 1.3 million per year. Very minor, maybe felt by humans, no property damage, just light energy release. Magnitude of greater than 9 or less than 1 per year. These are the largest recorded earthquakes, and the destruction is over extremely large areas. The most recent one was the one in Japan in 2011 with a magnitude 9. With the meltdown of their nuclear power plants, the tsunamis that hit Thailand that resulted from this. So large, wide-scale devastation. It is important to note that it does not accurately measure the magnitude above a Richter value of 8. The equipment is just not capable of that at this point. The energy release is much too high. And for reference, the atomic bomb dropped on Hiroshima, it had the energy equivalent of a 4.9. Okay, so you look at the number of earthquakes, anything of 5.0 and above actually is more damaging in terms of physical damage than the atomic bomb. And this is just a comparison of the Mercalli, the Richter, and then what's called a moment magnitude. The moment magnitude isn't really used very often anymore. And this is looking at just some numbers of destruction from a variety of natural disasters, especially in the Asian Pacific area. So you can see temperature, drought, even storms don't even compare to the amount of money and damages done by earthquakes and tsunamis related to earthquakes. So why is Asia and the Pacific so impacted by these? Well, these areas, the large area of the world with long coastlines, there are many tectonically active zones. ton of subduction zones because of the Pacific Plate movement and the Indian Plate collision. It's also a large area subject to monsoon climate, which would create a lot of typhoon occurrences. There's very high population density in these regions, very large cities, but without the necessary strict building regulations that they need everywhere. And also large areas that are underdeveloped and they lack the ability to build the infrastructure able to resist these forces. So factors that determine the degree of an earthquake and destruction are the magnitude, the duration, how long does it last, the nature of the rock and soil in the area. Okay, if you have a very stable, competent rock and soil, it's probably going to be less affected by an earthquake than a very loose soil or a sandy region. Proximity to populated areas, obviously less populated means less man-made materials to fail and less human beings to be impacted by any failure. The susceptibility of buildings to earthquake shaking. Our technology is getting better at building facilities that are able to withstand earthquakes up to certain levels. Proximity to coastlines. These are subject to tsunamis. And then proximity to mountain ranges. The destruction of earthquakes can be caused by the shaking of the land and the seismic waves. And this can cause liquefaction of saturated soils, creating landslides, mud flows. Fire due to breaking or ignition of natural gas pipelines, inland flooding due to destruction of dams, coastal flooding due to tsunamis, the landslides, and ground subsidence, basically the vertical collapse of a landscape due to liquefaction, due to a breakup of material. So this is just showing some destruction in Chile and Turkey from some recent earthquakes and just the impact it's had on the buildings there and the infrastructure. This shows damage due to soil liquefaction. So these are buildings that were actually not shaken apart. If you look, they're still 100% intact, right? They've just sunk into the ground and fallen over. This is because the soil here was so saturated with water that when the earthquake happened, basically the soil grains were all suspended within the water that was trapped within their pores, and it created a mud. So this was believed to be a competent soil is actually now basically acting like a liquid. It can no longer provide the structural support necessary, causing these buildings to collapse due to the lack of supports. I'll post the links to these videos. Lots of really good videos. Here's an example of fires caused by the earthquakes, Sumatra, and then Japan again. The infrastructure is just so heavily damaged that pipelines, gas lines were destroyed, and then water pipelines were also destroyed, meaning there was no way to put out the fires then. Collapse of dams. This is an earthquake in Taiwan in '99 that destroyed some dams and actually then flooded downstream. So the earthquake itself wasn't the problem. The problem here was the failure of a dam system because of the earthquake. Okay, we mentioned tsunamis, so now let's kind of discuss the impact of these. So these are large ocean waves that occur when a large subsea fault ruptures upward. So this is where it moves vertically upward, displacing enormous amounts of water in all directions. This creates a ripple effect. Tsunamis can travel at up to 500 miles an hour in the open ocean. They slow down as they get closer to land because of the friction with the sand at the base. But in open oceans, they actually go unnoticed because of the depth of the ocean floor. So they're moving at a speed of 500 miles per hour, but in the open ocean, there's no friction to really make that wave movement visible, that it is extremely hard to determine where a tsunami is until it starts to approach shore, until it starts to impact this bottom material here. As it approaches that shallow depth, tsunami height increases up to 100 feet in some instances. And this surge, because of its height, it actually then is able to flood several kilometers inland, depending on the topography. If you have a very low-lying, very even topography, it can move several kilometers inland and then backwash all of that back out. This is the Japanese tsunami after the earthquake of 2011. I will post that link for you to see. It's really impressive to watch the aerial footage of this. So the earthquake earthquake in Japan in 2011 was the fourth largest earthquake on record, with approximately 16,000 deaths. And most of the deaths, like I said, were not from the actual earthquake. A significant number were. Many of them were from the tsunami that occurred. So what happened was we had a magnitude 9 happening right where either the Eurasian or the North American plate, it's still under discussion which plate is right here. The Pacific plate was subducted under, and there was a significant energy release just off the shore of Japan. So the actual earthquake epicenter was actually offshore. Oh, sorry. And so the actual land vibrations caused significant amounts of damage, but the tsunami that approached then afterwards, because of the offshore location, this is what really did the most damage. Here's just a look at the Indonesian earthquake. This tsunami killed 230,000 in 14 countries. This shows you the epicenter. It's where the India, Australia, and Eurasian plates all meet. So this happened just off the shore of Indonesia here, and actually created ripple effects. So I think it was right here is where this occurred. And you can see that the energy actually rippled out basically to the tip of Africa here. It's an example of some landslides that occurred because of earthquakes. Most large earthquakes are associated with convergent plate boundaries and transform boundaries. There are two major areas of earthquake activity. One is the circum-Pacific belt, so basically that whole region around the Pacific plate. These are ocean plate, continental plate subductions, or ocean-to-ocean subductions. There are also a few transform faults along the continents, such as the San Andreas, where plates are kind of sliding past one another. The second is the Alpine Himalayan belt. This is continent-continent collision and ocean-to-continent subduction with the transport faults on the continents. So here's just looking at the circum-Pacific belt, and then you see the Alpine Himalayan belt. So this just shows how subduction, convergent boundaries create the earthquakes, and then erogenous or orogeny activities of the collision boundaries can actually create earthquakes. This looks at intraplate seismicity because it is possible to have fractures and movement within what is considered to be a stable plate region. So obviously California is right along that circum-Pacific plate, so it has a high seismic hazard. But if you look, especially in the Midwest, the most stable part of the Earth, or of the United States interior, it's very low hazard. There is a known fault right around here that creates some activity. There's actually an earthquake here when I was in undergrad that I felt here in Ohio one year. And then here in Jamestown, it's a fairly low hazard. There's a little bit of green up here, and again, that's because of that still active fault system up outside of Buffalo. This is showing earthquakes with magnitudes of greater than 3.0 since 1974. So like I said, there's a very active zone here. A little bit right outside Buffalo, a little bit in northern Ohio. There's another fault zone that's known in Virginia. Okay, the Reelfoot rift system, that's the one that's there. So this is a very active rift system within the U.S., which causes most of the earthquakes actually felt within the Midwest and within the Mid-Atlantic region these days. And we have a fairly good idea of the strength of the earthquakes that occur here. So magnitude 7.7 in 1811, 7.0 in 1811, 1812, 7.5, another 7.7 in 1812. So that gives us a pretty good indicator of how violent another large-scale earthquake in this region would be moving forward. And this shows an earthquake in Charleston, South Carolina in '86 with a magnitude of 7 and 60 people were killed. And then here between Messina, New York and Cornwall, Ontario in the St. Lawrence River Valley, there was an earthquake in 1944 with a Richter magnitude of 5.8, and that is the largest earthquake that has occurred in New York to date. And that, even so, that was still northwestern. Oh, no, sorry, that was right outside Erie, wasn't it?